So, welcome back. Where we left off was the notion of an orthogonal, two vectors being orthogonal. So the thing that we want to look at next is the notion of orthogonal and orthonormal sets. So let's first define these two terms. So a set of vectors, yeah, and I have p vectors here in Rn, is an orthogonal set if any two of them are orthogonal to each other. So the dot product of ui and uj is equal to 0 for all I not equal to j. So one way to think about it is each of these vectors are perpendicular to each other. And an orthonormal set is an orthonormal set if S is orthogonal. So it has the property that each of these vectors are perpendicular to each other, and we impose the extra condition that each vector in your set S, oops, I erased too much there, orthogonal set, each vector in my set has length 1 or norm 1 for all I. So an orthonormal set is an orthogonal set where all the vectors have a specific length. And you've seen these things before, actually. E1 through En is actually an orthonormal set, is an orthonormal set in Rn. It's clear if you think about this in R3, the standard basis elements, they're all perpendicular to each other in R3, and they all have length 1. So this would be an example of an orthonormal set. Let me give you an example of a set that has one of the properties, but not both of the properties. So here I have two vectors, 1, 0, 0, and 0, 1, 1. And I claim that this is an orthogonal set, but not an orthonormal set. So we'll just check two of the properties, right? So let's do the orthogonal check. Right, so we'll just compute the dot product. And since we only have two vectors, we just have to check that they're orthogonal to each other. So we have 1 times 0 plus 0 times 1 plus 0 times 1. And that indeed gives me 0. So this part is okay. Let's check the orthonormal part. Orthonormal check. So we need to compute the norm of each vector. So let's compute the first vector, the norm. So you take 1 squared plus 0 squared plus 0 squared. You take all the coordinates, you square them, and then you take the square root, and we got 1. Okay, so this is actually the correct length. It has norm 1. It's a unit vector. But if we try the second vector, I have 0 squared plus 1 squared plus 1 squared. I get the square root of 2, and this is the incorrect length, because I wanted this to be length 1. Looks like I misspelled length, so let me fix that. There we go. So we have a set that's orthogonal, but not orthonormal. Okay. Now the nice thing is that given any orthogonal set, you can actually, from that set S, make an orthonormal set. And the basic idea is your vectors are already perpendicular to each other, so you just want to rescale the vectors so that they all have the correct length of, in particular, length 1. And how do you do this? Right? Let's say that you have a set of vectors that's orthogonal. Then we're going to make a new set of vectors from this. And the way that we're going to do this is we're going to take 1 over the length of the first vector and use that as a scalar to multiply my vector u1. Then I'm going to do the same thing for my vector u2. And I'm going to move all the way through all my vectors. So the length of up. And I'm going to multiply it by the vector up. So you notice that I'm taking a vector and I'm multiplying it by a scalar. So I haven't changed the direction of any of these vectors. They're still orthogonal, but I've rescaled them all. Okay, so let me put that in here. Oh, so let me finish off the sentence here. This is actually orthonormal. This is an orthonormal set. And what we have is that, undo that part. We have that the vectors are rescaled. So have length 1. And this process by which you turn a vector and you rescale it so its length is 1 is called normalizing. Called normalizing. Okay, so let's look at the example that we were just playing with right here. We saw that this is an orthogonal set, but not an orthonormal set. But according to this procedure, I can now find an orthonormal set. So this set is orthogonal. So I am now going to just follow the procedure lined above there. Here, I'll just move that so we can see it. We have S star is going to be 1 over the length of that vector. And in fact, we did this work already, right? Because the length, this is the length of the first vector. Maybe I'll put that right here. This is the length of U1, and this is the length of U2. So S star is going to be 1 over 1 times the vector 1, 0, 0, and then 1 over root 2 times the vector 0, 1, 1. And then this just becomes the vector 1, 0, 0, and the vector 0, 1 root over root 2, 1 over root 2. And there we go. This is an orthonormal set. And I'll put that there. Is orthonormal. So there we have now a new notion of describing a set of vectors. Let's go back here. We have a new notion of orthogonal set and orthonormal set. And once we have an orthogonal set, we can make an orthonormal set. So in the next part of today's lecture, I want to tie orthogonal sets with linearly independence, and then we want to tie this to bases. So we'll take a pause here, and then we'll get to that part in a minute.